bow out a little early. So once again, I appreciate everyone joining us this morning. I think we have a really good webinar in front of us here, some excellent speakers that I'm really excited to share with everyone. Want to just remind everyone, for those who have just showed up, if you have questions, there's a chat feature within the app. Please use that chat feature for any questions, comments, anything. We'll look at those at the end and kind of address those questions as they come up in kind of a panel, and then we'll kind of take things from there. But I'm going to go ahead and jump right in. So what is it about additive manufacturing that or new materials, I should say, that really, I think, gets people excited? What is it that I think draws people attention into new and strange and maybe mysterious materials? Like, in pop culture, we hear, materials called vibranium and adamantium, and they're typically completely indestructible or lightweight and stronger than steel, and we've kind of developed this mythos around new materials and new products that I think people wish existed but don't. And so what is it that really captures the human imagination around these materials, and what helps us define kind of the different stages of human development as part of those materials? I mean, if we talk in history, we look back and we say, okay, we have the Stone Age, then the Bronze Age, then the Iron Age, now maybe the Silicon Age that we're in now. Why is it materials really define the different stages of human advancement, and what is it about that causes, I think, excitement in humans? I mean, even in science, we hear about some of these kind of mythical materials like graphene that's 100 times stronger than steel, and carbon nanotubes that have a higher tensile strength than anything that exists. Why is it then that we don't have buildings made of these materials? Why is it that we don't, make suits of armor that are completely impenetrable? And it really comes down to, if you can't make it into something useful, it doesn't really matter. I mean, if we go back to those pop culture references, there isn't a pop culture reference that really talks about a material as just being a material. They always talk about its properties and then where you use it. So, adamantium, I mean, it's the claws that are completely indestructible, that are, infused with his bones. Or the Valerian steel is stronger and can cut other swords in half. It talks about the use and the application space. And that's something that I think there's really a difference between just being able to address new materials and talk about great new properties in a maybe lab setting versus actually having impact on the culture and having impact on humans and what we do. And I think that's really where I'm excited about additive manufacturing. And additive manufacturing in particular, I think, is drawing and bridging that gap, hence the name of the series that we do here, of bridging the gap between, pure developmental science and real usable applications, where you can actually go and take a component made of some brand new material that has properties that have never been seen before, and you can put them into practice in a shorter period of time, and in reality, way faster than it's ever existed before. And I think that's what personally gets me excited about new materials and additive manufacturing in particular. When I was doing research in graduate school and really developing new materials there, it was so hard to control and to transfer that knowledge into something that would be useful for industry. To whereas we're now developing materials where we're going from a development concept of a new material and going into production on a component within 2 years, which is an incredibly fast timeline compared to what has really happened within human existence in the past. And that's really where I get excited about, the new materials that we're looking at. I don't want to toot Elementum's horn too much. A lot of you know who we are and what we do, but I feel remiss if we don't talk about it a little bit. but new high-strength aluminum alloys, and not just alloys based off of the alloys that already exist, but going beyond that into materials that are competing with beryllium and competing with some of these mythological materials that are very hard to produce or make or use. And then we go into other very difficult materials, very high temperature nickel superalloys for all sorts of application spaces. And then even in the refractory materials, like rhenium. We've been printing rhenium recently, which if you had told me that we'd be making components out of rhenium and then hot fire testing them within 6 months, if you had told me that 10 years ago, I would have probably told you you're crazy. And so I think that's the really exciting part about additive manufacturing and the new materials that we're bringing to the table. And that's why I'm really excited to introduce the speakers that we have here today. A little bit about Elementum's relationship with these different people. Elementum has a lot of relationships across the entire industry, but certainly we've been working with these gentlemen quite a bit. Jamie, I mean, we've been working with 6K products now for, only about 6 months, and really working on different things and working with the rhenium that we've been printing was with them, if you saw that LinkedIn post. So excited about introducing Jamie. Doug Hoffman was actually our first customer at Elementum back about 8.5 years ago. So that was a long time ago at JPL. And Tim Smith, certainly I think very little introduction is necessary for Tim Smith. I think a lot of us understand the impact of GRX 810 and the excitement in the industry for new high temperature nickel superalloys. So with that, I'm going to go ahead and hand things off to Jamie, and he'll jump in and tell you about the great new materials that they have going on there at 6K. So Jamie, let me hand over the presentation to you. Perfect. Thank you, Jamie.
Okay. Good morning, everyone. Thank you for participation in the webinar, and thank you, Jacob and Elementum for setting this up. This is a great opportunity to discuss some of the great things that we can do as an industry in terms of additive manufacturing, and specifically with 6K additive, where we might be able to fit into bridging some of that gap by providing some of the materials that may not be readily available. I always frame this by saying 6K additive is we're great at making materials, but we're not alloy designers or anything like that. So we always like to know what people want, and then we like to figure out how we can make them. So I think that's where we really fit into this, and really fit into the additive world. Besides, making some of the more common grades of tie and nickel that are very common in additive manufacturing, we like to hear what people would like to do with it and what we think the technology can do as a whole to advance, to your point, to bring some of those things that seem like they're off in the distance to fruition. Just a little bit about 6K additive in general. We are part of a larger company called 6K Incorporated. We generally have two folks that are two divisions that most folks know about. That's the additive, and then we also have the other group, which is the energy group, which makes battery materials. Of course, this is focused a little more on the additive group, so I'll focus a little more on that. We are about 75 employees. We actually have 4 locations now, with our global center of manufacturing being close to Pittsburgh, Pennsylvania. As a group, we have about 126 active patents. And I think one of the things is, besides the manufacturing portion of what we do, we also have an R&D center of excellence, which is located in North Andover, which is part of the 6K Incorporated group. So besides leveraging our own manufacturing expertise, we can also leverage a lot of R&D work from the North Andover group, which includes not only just design of materials and the processes, but also design of equipment to facilitate those processes. We are a full service we are a full service powder supplier. I think the best way to describe us is probably like the fourth bullet down, which is a wide spectrum of quality metal powders from sustainable sources. But we also have that R&D arm, and there's a variety of different ways that we can approach making these materials. The core part of the core technology that facilitates everything that we've built around these manufacturing processes is the Unimel Plasma system itself. It's a microwave-based plasma system, which I'll talk about in the next couple of slides of why it's unique. But I think it's always very important to understand, and there's probably a large group of people on here that have probably heard it before, but I don't think everybody always completely understands. Our plasma, we're not doing any atomization with our plasma. We are simply doing spheritization. So we're simply doing the step that facilitates a morphology of powder that allows these things to be used in additive manufacturing. Now, there are some benefits that come along with that, in that we can, improve cleanliness, particularly interstitials for things like gases. But the key thing is that we can take a lot of different types of materials and input it through the plasma and melt each of those individual particles and allow them to become spherical and give us the properties that are important to most of the additive manufacturing machines when it comes to the utilization of powder. So we call it a volume in, volume out process. Very important to understand that in this process, in that core process, we're not doing any size change. It's only shape change. The microwave plasma itself is sort of unique in that it is a little bit different than what conventional inductively coupled plasmas or some of the other technologies that exist out there, because it's actually a little bit cooler plasma, and that affords us a couple of benefits. So we say the core of our temperature is, and it's the rub on our name, is 6K. It's 6,000 Kelvin is what the core plasma temperature is, and that's a little cooler than what some plasmas run. But it also is it's a much larger density of plasma and a much larger working zone in the plasma itself. So a few things that affords us. It's highly stable. It has a great temperature uniformity throughout the plasma itself, from the core outward, and it also is highly energy efficient. So the energy that you put into the plasma system, the microwave couples, and the energy that from the microwave is about 85% efficient to the plasma. What all that does is it gives us a really nice processing zone for a wide variety of materials. So we have a pretty broad-based product offering, and it's facilitated by the fact that this microwave plasma is so controllable and that we can create a nice material processing zone within the system itself. Sorry, I'm just trying to advance the slides. Okay, here we are. So this is sort of a demonstration of the breadth of the power of the plasma. We always like to show this because it allows us, or it shows that we can process a wide variety of materials that have a wide variety of melting temperatures. So within the plasma system itself, we spherize everything from aluminum silicon, so Al10, very common in additive manufacturing, all the way up to tungsten. So a wide variety of different melting temperatures. And we can be successful with all of these because of that control that we have over the microwave plasma system. And there's a few different ways to control it. We can control the power, and we control the space where we actually inject the material into the plasma. But what it allows us is again, anywhere from a very low melting temperature material all the way up to a very high melting temperature material allows it to be processed through this system. So again, when you're thinking about material design or alloy design or what are the things that can be done, this gives you some idea of the wide range of materials that we can process on our system. Okay, the total capabilities of the system itself. Oops, sorry. Of the system itself. So I mentioned earlier that we do the core alloys, the nickel alloy the nickel family of alloys, stainless steels, titanium based. But we've also expanded out into starting to commercialize some of those refractory alloys. And while I won't go into the whole capability matrix, you'll be able to look at that through the recording. We have a wide variety of options of raw material inputs that we can get to those spherical powders. And so some of our core focus is mechanically milled. So where we're taking particulate materials and making them the right volume via mechanical milling. We can take irregular powders. So whether it's from some other atomization technique or chemically reduced powders or even used powders. Also we have the ability to do hydride convertible solids. You'll see a lot of that. So for tantalum and tungsten and niobium based alloys, we can do that. We also have the ability to mechanically alloy this. So this is where a lot of the design stuff can really come into play, which is where you can take a look at what are things that we could put together that might not be able to be conventionally put together, and kind of agglomerate them together and then sphericize them in the Unimelt reactor. But any of those feedstocks are good to end up with a spherical material for additive manufacturing. So a little bit of the focus in the second half of this presentation is just the refractory metals in particular. I think this is a space that's gaining a lot of momentum, and I think we all believe that additive manufacturing is a really good space for this. You have these very high melting temperature alloys. They're a little more dense. And the characteristics that make them so good for some of the applications that we're looking at also make them very difficult to handle in not only the production of the materials themselves, but also the manufacturing techniques. So I think that when we look at this space in particular, additive manufacturing and the Unimelt process kind of bridge that gap to unlock the potential of these materials and really get them into parts, into applications, into wider spread applications. Some examples of some materials that we produce on a commercial basis now. We actually make tungsten. I think it's probably the most commonly printed refractory metal. I think we see the most people working with it out in the industry now. It's probably the most readily available just in general, but there's a lot of different particulate feedstocks that you can find in the tungsten. And we have the ability, again, to sphericize that and get it to a place where it's useful for additive manufacturing. So correcting all the key components, the flow, the densities, to make it useful in most additive manufacturing applications. Here's an example of a part, a Collimator. This is courtesy of 3D Systems, but you look at a part like this and probably not going to be very easy to manufacture anyway, but via additive manufacturing. So you think about this type of application. Again, additive really has a nice fit in this space. Another one, this is from a little bit different feedstock. This is a C103, so a niobium-based alloy from the hydride dehydrate process, which creates a nice blocky kind of angular feedstock, but again, not good for additive manufacturing. But again, with the Unimelt, we can convert that to a nice spherical powder and make it very useful for additive manufacturing. Again, nice spherical powder particle, good flow, good AD, good tap density. So again, just unlocking some of those possibilities. And I think most people probably know that this is typical in hypersonics, where you require high melting point. These parts are courtesy of Castheon. Low coefficient of thermal expansion, all those things that are important for things that might move really fast. Again, unlocking some of those possibilities. And again, I use these as examples, but I always, like to say, we like to design and are very good at designing the processes to make the materials. But we're always looking for people with ideas of what do we need to make, and then we can figure out how to make it and get it into some of those applications. The last thing that I would be remiss in talking about is, I think everything that we do at 6K Additive is, we think about the environmental aspects of things. And I say that, and we've done a life cycle assessment on our process, and the improvements over some traditional processes. But I think even beyond that, we like to talk, particularly in the AM world, about making sure that we keep this eye towards sustainability and towards the environment. And that 6K Additive it looks very closely at being able to help the end users recycle all of the waste streams of this. It actually ends up becoming a nice circular economy, because whether it's spent powder or failed parts or builds, we know that those are all issues that not only have cost implications, but also have implications to the total sustainability of the additive manufacturing process. So I like to throw that out there and say that in the development of all these alloys and all these different techniques, we like to think about ways to try to bring back the materials that can't be used in the processes, and make sure that we have a place for them to go, and that they don't just end up in landfills or worse yet, sitting on shelves for decades, and that it becomes somebody else's problem in the future. So with that, I'll turn it back to Jacob to move the webinar along, and I'll be happy to field questions, at the end of the webinar.
Great. Yeah. I really appreciate that kind of overview, and certainly I think we see a number of application spaces where how do you make the powder tends to be something that is a limiting factor. So again, if you have questions, please put them. I think there's even a questions tab where you can submit questions to the panel and all of that as well, and then we'll address them at the end. So I appreciate it, Jamie. All right. I'd like to introduce our next presenter. Just one moment so I can introduce Doug. So Doug from JPL, if you would give us a short introduction, and then we're going to jump right into your presentation.
Great. Hi, thanks, Jacob. I'm Doug Hoffman, a senior research scientist and the section technologist for mechanical fabrication and test at JPL. So let me share my screen. All right, well, let's just get started here so that Tim has time to talk after me. I'm going to be talking a bit about the 3D printing alloy development at JPL. Everything I'm talking about is actually from before the pandemic, when we were doing a lot of this work. So we actually have several years worth of additional work that we're kind of chewing through. But this gives you kind of a snapshot in time from what we were doing up until the beginning of the pandemic. I think additive manufacturing is playing a significant role in flight projects and R&D efforts at JPL. This is just sort of a picture giving a snapshot of some of the things that we are working on, just a wide variety of applications. As you probably know, the Jet Propulsion Laboratory, we're NASA's federally funded research and development center with a focus on robotic space exploration. So we have a lot of very unique missions and a lot of one-off applications for materials in extreme environments. So you can really see that flow down into the kind of parts that we're interested in manufacturing and the kind of materials that we need to be able to use in those applications. So our additive manufacturing group is joined with our materials development group. So we have a group called the Materials Development and Additive Manufacturing Group that focuses on conventional metallurgy and alloy development, computational thermodynamics, as well as both metal and polymer additive manufacturing, all with the objective of being able to produce parts to enable extreme environment exploration. I should just mention, that we do have some slight heritage with metal 3D printed parts. So, we've got some very unique challenges. This is our Mars rover Perseverance, and we flew 12 3D printed parts on Perseverance. I'll show in the next couple slides. But here's the CAD model of it, as well as a picture I took of it being assembled. So this will just kind of give you an example of the kind of applications that we have for advanced materials and for additive manufacturing. So the two infusion points that we had on Perseverance were in the Moxie experiment and in the Pixel instrument, which you can see here on the Rover. So the Moxie experiment, as you may know, was the first demonstration of planetary in situ resource utilization, or ISRU. It was a tech demo payload to demonstrate the production of oxygen from the CO2 atmosphere on Mars. And the preheater assembly in Moxie was a pretty complicated part with internal features that we decided sort of late stage was a good infusion point for metal 3D printing. And then Pixel is a spectrometer that you see on the right. And in this case, we were using additive manufacturing to produce a pretty complex housing that went over the Pixel instrument. So here's the images of the actual flight hardware that we produced for Moxie and for Pixel. So Moxie was sort of an internally generated part that was printed on our own EOS M290 out of Inconel 625. And there were several parts of this preheater assembly that you can see printed here. One part in particular that had internal cavities in it that you can see with the CT scan on the right. So this is a part that sort of was a pathfinder for being able to produce flight hardware from design all the way through qualification and infusion. The part at the bottom is the dust cover for Pixel, which is a very complex part to manufacture out of sheet metal. Has sort of this hollow rim that goes around it, and then it has this thin walled titanium cover that goes on the instrument. So this was printed in E-beam out of Ti 6.4, chemically etched and painted before it was installed on the Rover. So two kind of different applications for additive, both really demonstrating the utility of additive for flight hardware. And then I think this picture is just, I guess, my favorite. This is the 3D printed Ti 6.4 dust cover for Pixel on the surface of Mars on the Perseverance rover. So if you ever see a picture of the Perseverance rover, you've got that big flat white panel right there. You can point that out to people and say that is a 3D printed part sitting on another planet. So it's kind of a big success from our infusion, and it kind of demonstrates this TRL9 use of additive manufacturing. Of course, this isn't the end of the story. This was sort of our first infusion of metal 3D printing all the way through a flight project, and hopefully it'll be one of many in the future, including hopefully some in the future that involve new materials that we are developing with ourselves and our partners. So if you kind of look at some of our mission concepts in the future, these are missions that haven't flown yet, but hopefully will fly someday. This is our EELS concept for exploring the moon of Saturn, Enceladus, which is sort of this worm-like or eel-like rover that will hopefully crawl through the vents on Enceladus to access the subsurface ocean to look for life. But these are the kinds of environments that we are dealing with at JPL. One day we're developing parts for Mars. The next it's a lunar rover. The next we're developing prototypes for a moon of Saturn or Jupiter. So this kind of gives you an idea of why we have to develop new materials and manufacturing technologies to access these, these extreme environments. So here's just a look at the EELS rover and some of the prototypes that have been built, where we have been using additive manufacturing for prototyping. not only for some of the joints, but we've even 3D printed the screws on the EELS rover for going through snow using our Formlabs 3D printer. These are Ti-6-4 parts that are printed on our M290. So you kind of see that we work in both sides of the spectrum, from flight applications down to prototyping, and we work heavily with our robotics group. Mobility for rovers is an area where we see a lot of promise for additive manufacturing. So we see here some compliant wheels for rovers. So we've been exploring how do you use additive manufacturing for innovative mobility systems. So this is a cool example of a compliant wheel that was 3D printed in a single piece using laser powder bed fusion. It's printed in a stack, and then you remove the supports, you compress the stack to pop open the mesh of the wheel, bolt it together, and you've got yourself a compliant wheel that can be made out of any material that you can get into a laser powder bed fusion printer. So this kind of gives us new and interesting capabilities for mobility. So moving on, we've also spent a lot of time looking at the design for additive manufacturing. We've got scientists at JPL that work on design, topology optimization, and hybrid manufacturing. So this was a collaboration between JPL and Autodesk to envision how design for manufacturing and topology optimization could be used for future spacecraft. In this case, this was a Europa lander for the moon of Jupiter. And this was, you see sort of the organic looking frame. This part was, designed for hybrid manufacturing that includes combinations of additive, subtractive, and castings all together to make a extremely low density, stiff, topology optimized lander. This is sort of was a pathfinder for where could you take this technology if you are sort of agnostic about the manufacturing route, but you look at the design that is enabled by computational methods, and then you apply manufacturing constraints like additive, casting, and machining. What can you do in terms of spacecraft design? So this was a really cool pathfinder part that hopefully will flow into some of our future missions as we try to reduce the mass, which allows us to fly similar missions in smaller launch vehicles. So just to give you a snapshot of our additive manufacturing, this is our metal additive manufacturing center at JPL. I know, most people, this would not be that impressive because we've got just a small number of printers. We've got 2 EOS M290s, 1 EOS M100, and then an RPM 222 4-hopper DED. But what's great about our additive manufacturing center is that we have a qualified manufacturing process compatible with the NASA 6030 standard. So we've got a flight qualified process for aluminum 6061 Ram 2 and for Ti-6-4, so that we can produce flight hardware through this process using our additive manufacturing center. So our team at JPL, spent a long time setting up this facility with the goal of being able to produce flight hardware for NASA using additive manufacturing. And this has been a multi-year effort to be able to stand this up. Of course, in the center, we also have alloy development capabilities with our multi-hopper DED and our M100. And we partner with dozens of universities and national labs and commercial companies to do further development. So some of the ongoing additive materials activities we have at JPL, we do magnetic materials for thrusters. We're looking at high strength aluminum alloys, copper alloys for CO2 reduction. We printed amorphous metals, metal matrix composites, ceramics. I'll show some ultra hard cutting tools that we've been looking at for excavating cryogenic ices. And of course, we've been working for over a dozen years now at this point on functionally graded metals, which we have identified a lot of beneficial applications for, but it's very difficult to infuse those into missions because of the mixed metal compositions in functionally graded metals. So here is some work that we've been doing on our DED. This is some 3D printing of Hyperco for some thruster applications. And so I'm sure the video is running choppy on your screen, but it's a cool time lapse of printing of one of these Hyperco thrusters. So, typically we can 3D print with our DED into near net shapes, and then we do finish machining using, our machine shop, which is right outside our additive center. And we can get really unique magnetic properties by controlling grain size in our DED, if not by controlling composition. Just this week, we printed another bimetallic magnetic part that takes this work even further by mixing two materials together. Moving on, one of the things that we've been working on is looking at how to develop cutting tools to cut through cryogenic ices if we land on Enceladus or Europa. So one of the alloy development projects that we had starting back in 2017 was the development of 3D printing excavating tools for robotic arms. And so this was a very difficult challenge because we don't have very stiff robotic arms that you would expect on a giant KUKA or a drilling rig. So we have to design robotic arms that can trench and excavate through ice on flimsy robotic arms using low power, and they can't get stuck because otherwise the mission would be over. So we spent a long time developing new designs and then fabricating these cutting tools out of different materials. So we collaborated with pretty much anybody that could produce new materials for cutting tools. So we printed some of these cutting tools out of zirconium-based metallic glass with Heraeus, and we worked with Elementum on printing metal matrix composites and tool steel, which you can see in the image there. So what we're doing here, as you see if the video runs on this next slide, we're trenching through some ice simulant using an amorphous metal cutting tool. So we're measuring basically the mechanical specific energy of these cutting tools and looking at the cutting performance of these tools as a function of their design and the material that they're manufactured out of. So this really gave us a chance to sort of fix the design and then look at the effect of material on the cutting performance. So here you can see 5 different cutting tools made with various materials from, Inconel metal matrix composites from Elementum, Ti-6-4, maraging steel, tool steel from Elementum, 316, and we have measurements of cutting performance in our simulant for all of these cutting tools. So this kind of gave us a good idea about how we drive this technology further. We eventually went to tungsten carbide, which is that curve right there. So we've been able to print tungsten carbide embedded in steel to get really impressive performance. So some of the alloy development things that we're really interested in is developing metal matrix composites. And so here's 3 examples of the metal matrix composites that we develop. There's in situ, where you can melt phases together and you can form dendritic phases that solidify from the liquid. You can do hybrid composites where you partially dissolve particles, reprecipitate them, and you've got 3 phases present. We also look at ex situ composites where you have insoluble phases inside of a matrix. And these can all be printed both with powder bed fusion and with DED for various applications. We wanted to make this cutting tool out of a titanium carbide metal matrix composite in Ti-6-4. So, part of doing alloy development is trying to learn parameters. So we worked with Elementum to try to develop Ti-carbide loaded Ti-6-4, and it didn't work very well in powder bed fusion with high loadings of titanium carbide, which we were hoping to get, 40, 50% loadings. So, this is part of the process of doing alloy development is figuring out what works and what doesn't work based on the available parameters. So we switched to DED to be able to try to do these Ti-carbide loaded Ti parts. We're able to get up to about 30% loading of Ti-carbide before we start getting significant cracks in the Ti-6-4. So we're able to do, functionally graded Ti to Ti-carbide alloys. And with DED, you're able to control the melt pool to partially or fully dissolve these Ti-carbide particles to create metal matrix composites with really innovative microstructures. So here you see some micrographs of partially dissolved and reprecipitated titanium carbide in Ti 6.4 parts. So this is kind of one of the most exciting things that we have developed with DED is multi-material metal matrix composites that combine titanium and titanium carbide in functionally graded ways so that you can produce ultra hard titanium alloys as well as very high melting temperature titanium alloys that are loaded with Ti carbide. So one of the things we demonstrated is we made cutting tool inserts out of these Ti carbide parts, and then we did the same experiments where we did cutting performance using these inserts to demonstrate that we could actually develop Ti carbide metal matrix composites that have pretty excellent cutting performance compared to tungsten carbide, which was really surprising to us. And the advantage of using additive is that you don't have to make inserts. You can print these directly on your cutting tools so that you don't have to worry about bolts, bonds, or brazes. So, this is one of many of the areas that we're working on where we're trying to use alloy development to get us a new capability that hasn't previously existed. And the reason we're doing it is because our unique missions require that we go to extreme environments and innovate with the design and operations of our spacecraft and rovers. So that's my last slide, and I'll, if you guys would, are interested in emailing me, reach out, and I'll be done and turn it over to Tim.
Great, thanks, Doug. Sounded like Tim might be having a little bit of technical problems, but we'll try and hand things over here. He may have frozen. So in the meantime, while he's trying to get back in, why don't we go ahead and field a couple of questions, and then we can kind of dive in. So one of the questions is about cost. Generally there's a concept of free complexity, and we've talked a little bit about that. And so I want to talk and dive into that difference in new materials as well. So generally, what at least we found as being successful approaches to that question of cost really tends to be centered around, well, if you're trying to machine rhenium, there's very few places who will do it. And when you go to do it, it costs something like $400 an hour. And so there are quite a few materials, and metal matrix composites, I think, are very, very much the same way, very difficult to machine. I mean, if you're up at 10, 15, 20% ceramic, it can be very difficult to produce these in any other way. And so particularly for new materials like these, there's a different cost modeling of the performance difference here from these materials is significant enough that it would be almost impossible, if not impossible, to make these materials any other way. Any I think, comments on that, Doug?
Yeah, I would totally agree. I mean, at least for our applications where we're sort of cost invariant, you can get away with, spending a lot on a one-off if it does something really unique. So one of the things that has been a struggle with additive is, commoditizing it out in commercial industry, being able to mass produce parts using additive, even when there is a beneficial geometry. You really have to be very selective about your additive parts with the current makeup of the commercial landscape, where the part really cannot be made any other way. So you mentioned these refractory metals that would be impossible to machine otherwise. You're talking, extremely large rocket engines or nozzles would just be extremely difficult to machine conventionally. These are great applications for additive. And, where you're going to see the future is how do you take novel materials and apply them to additive, where the benefit of using the novel material outweighs the additional cost of not only the qualification and the material production, but also the manufacturing and post-production of the additive part. So that's, you're already kind of seeing that a little bit. All right, there's Tim, he's back.
Hey, excellent.
Hey, yeah. Me out there first.
I want to address one more question before we get into Tim's presentation here, because I think it's one that's relevant and sets up the next conversation as well. As you know, these new materials and adding new materials and additive manufacturing in general is great, but what happens if you need to like really qualify it for a crucial application space? And again, Doug, I think JPL is kind of paving the way for that, in that you can't have a flaw that you discover when it's on Mars. So how do you address that? How do you address qualification of additive manufacturing? And that, you know, I think a lot of people are still afraid of additive, even though there are, I think, quite a few examples of additive being used in TRL 9 or, you know, similar.
Well, I mean, fortunately, the NASA 6030 standard is pretty robust. If you haven't read it, you can get a copy of it. But it describes how to set up a qualified manufacturing process for a different class of part that would be used in a flight mission. So that involves everything from, you know, qualification of the powder, the machine, coupon level testing of parts that are printed, as well as non-destructive testing on the part before it flies. So doing CT scanning, doing proof loading on it. So there is a whole process that you go through to assure that the parts that you produce with additive will, you know, work as intended, and you don't have unexpected consequences.
You know, it's interesting that you put it that way too, because I think that additive is held to a higher standard than a lot of other manufacturing techniques, because we're more comfortable with those other techniques, and that follows for me. But you know, in particular, CT scanning. I was talking to someone in a federal government position, and I asked, well, you know, the traditional part that's made, has that been CT scanned? And they're specifically saying, no, we won't go back and CT scan parts that have been made through castings, because if we find a flaw, then we have to ground the entire fleet, even though they've been being used for 50 years. And so I think there's a sense of additive as being held to a different standard of quality control, because it's a new and different and a technique that people just aren't as comfortable with yet. And so I think there's some interesting aspects with that as well. But with that, I'd like to hand things over to Tim, and I'll make you the presenter again here, Tim.
All right.
All right.
All right. Do you see a full screen? Full
Yes.
slide? Perfect. All right. Thank you everyone for staying on while I figured out how to get back in the webinar. But I want to present some of the work that we've been doing at NASA Glenn. My name is Tim Smith. I've been research here for about 8 years, and this is some overview of the high temperature alloy development that we've been doing here at NASA Glenn. So a little bit of background on the application that kind of drove this research. It came about through discussions with combustion researchers across the center who were trying to 3D print that combustor dome that you see on this slide. And they wanted to test it up to temperatures of 2000 degrees Fahrenheit or higher. And the materials that they had been using just weren't up to snuff really when they started hot fire testing their parts. And so they came to us and said, hey, is there a material that we can buy off the shelf that we can 3D print these components with and operate at these really high temperatures? And we kind of came back to them and said, we don't think so, but we would really love to set up a project here where we kind of explore new alloys that can operate at these really extreme temperatures that are also amenable to the 3D printing process. When you kind of look at the alloy systems that are available for temperatures of 1100 C or higher, there really isn't that many material systems you can tap into. Obviously refractory metals, you have your composites and CMCs, and then some other nickel-based superalloys, especially your galvanized strengthened alloys. And a lot of these really have issues with, one, they're either not easily 3D printed, or they have really troublesome oxidation properties like refractory alloys. And since we weren't going to be able to pick up a coating project on the side for like something like refractory alloys, we decided to not go with those. Instead, we started exploring this other class of alloy system called oxide dispersion strengthened alloys. In fact, back in the 70s, 80s, 90s, a lot of research was done even here at NASA Glenn on alloy development for oxide dispersion strengthened alloys. And really what an oxide dispersion strengthened alloy is if you can incorporate nanoscale oxides through your bulk metallic part, evenly dispersed, really a multitude of high temperature properties get significantly improved. Strength, creep, oxidation, and things like that. The issue though is how do you get those nanoscale oxides into your metal component? You can imagine with more conventional cast processes, once that metal melts, the oxides immediately float to the top, agglomerate, and are not equally dispersed in your part anymore. And so in the past, they would do this very expensive mechanical alloying step and hot compaction, and then your machining to finally get a finished product, and really ended up being too economically costly to really see ODS alloys get take off within industry. However, we want to take a look at oxide dispersion strengthened alloys again with this new manufacturing technique of laser additive at our disposal, and see if we can kind of bypass these expensive processes of the past and make ODS alloys just by printing them. The issue though is always how do you get your nanoscale oxides with your metallic powder into your 3D printer? And what we came up with was using this new high energy mixing technique called resonant acoustic mixing. What we can do is we can take the metal powder, which in this case, starting our research was nickel, cobalt, chrome, equal atomic. It's a very amenable alloy to 3D print and kind of creates a really nice foundation of this ODS project moving forward. So we took this nickel, cobalt, chrome powder and this nanoscale yttria particles, and we would mix it in these resonant acoustic mixers. And what happened was those nanoscale oxides would adhere and coat the metallic nickel, cobalt, chrome powder. And you can kind of see some SEM images on the bottom here. And if you kind of look at, the thickness of this type of coating, it looks like about 250 nanometers thick, roughly, that would get adhered to the metallic powders. Another way to look at it is the image on the left here is of an uncoated nickel, cobalt, chrome metal powder particle. And then you can see in the middle there, what it looks like after we coat it. What was really nice was that this process doesn't, heavily deform metal powder. With mechanical alloying, you take very spherical powder, and by the time you're done, it's almost like flakes or plates, and they don't flow very well. And when you try to 3D print that type of powder, you really introduce a lot of defects into the part because it's not a very spherical powder for 3D printing. In this case, however, we don't deform the metal powder particles, and in fact, what we have found is that the flowability appears to improve significantly after we coat it. And so it's a process, this coating process is really amenable to the 3D printing step. So we would take this yttria coated nickel, cobalt, chrome powder, and we would put it in our printer, and through some trial and error, we were able to find, parameter sets that evenly disperse that coated nickel, the coated yttria into our metallic build. The image, SEM image on the lower left here, you can kind of hopefully pick up these really fine black dots in the micrograph there. Those are not pores or porosity, those are actually the nanoscale oxides evenly dispersed into your metal component there. And you can see it doesn't really prefer grain boundaries or other locations. It really does appear to be, evenly and randomly dispersed throughout the metal part. And so we kind of proved to ourselves at this point that, hey, we can make ODS alloys with this coating step using 3D printing processes without, mechanical alloying. That's about right when the pandemic started, and we all got sent home for a while. And so colleague Chris Cantos and myself decided, we have a lot of these thermodynamic modeling tools at our disposal. We know we can make nickel, cobalt, chrome ODS, but there's nothing too special about that composition in terms of really optimizing high temperature properties. And so we wanted to take that foundational nickel, cobalt, chrome composition and alloy it to maximize its high temperature properties. And so we set out some goals for our modeling process, which was, maximize solid solution strengthening while maintaining it from, operating temperature to melting temp to room temperature, adding grain boundary carbides for strength, all while maintaining printability of the alloy composition. And so what we find is that, loose rule of thumb is that if your range between the liquidus and solidus temperatures, let's say, goes above 100 degrees Celsius, you're more likely to run into 3D printing issues like microcracking and things like that. And so we wanted to keep a narrow freezing range, and then obviously avoid TCPs or any intermetallic grains that might form on grain boundaries that would be detrimental. And so we ran a ton of simulations and really came to this optimized composition that we're calling GRX-810, as you see below. We were able to take that powder, successfully print it, and start doing some characterization of the microstructure. Some notable things that we found was we do see carbon segregation at the interface between the oxide and the metal matrix. We aren't sure, if that really has anything, any additional benefit to the properties, but it was an interesting observation that we could see with some high resolution TEM analysis. We also see the presence of niobium titanium rich carbides, which are those MC carbides. We wanted to strengthen grain boundaries, and so the simulations were successful there. And we also see segregation of chromium and tungsten and rhenium at the grain boundaries with this alloy. So we think that might help also strengthen and improve the oxidation properties of these grain boundaries. And then just looking at the atomic lattice, we show there isn't any elemental ordering or segregation. We do have a true solid solution matrix with this alloy. So we started to do tensile testing through a wide range of temperatures. Notably, it does have very decent cryogenic temperatures, high strength, high ductility, even with those nanoscale oxides incorporated into its part. But when we start to explore this alloy compared to your more conventional 718, 625, and even Haynes 230, what we find is that by the time you get to 2000 degrees Fahrenheit, you start to really see the benefit that these oxides have on the tensile properties here. And so you can see on that bar chart on the upper left, almost a 2x improvement in your tensile strengths with GRX-810 versus, your ROT 718 and 625 alloys. So then we started to do creep tests. And so this is creep curves to rupture at 1100 degrees C, almost 20 MPa, so very high temperature, low stress. And that red curve there is nickel cobalt chrome non-ODS. So just us 3D printing that nickel cobalt chrome powder that we had. You see, you get a handful of hours, it strains very quickly, and then it breaks on you. The brown curve is AM718 that was hipped and heat treated. Almost the same strain rate as nickel cobalt chrome, but you can see, it does have some longer life and ductility, better ductility, but still in about 20 hours, your parts failed. The light blue curve is actually AM625 that's been hipped, that's at an even lower stress, so 14 megapascals. And so we had to actually lower the stress to be able to put this curve on this chart here. And you can see, even by lowering the stress, you still only get a handful of hours with it. And then this purple curve here is your Haynes 230 raw alloy. Strains about the same as 718, but you do get better ductility. So overall, all these nickel-based alloys, they really can't handle this type of high temperature, and the part fails very quickly. This blue curve here is one of our original ODS alloys that we produced, which we were very excited about because, hey, we doubled the life compared to Haynes 230 with this ODS alloy. But I'm going to show the same curves now with GRX-810. And so you can see with this, optimized composition with the nanoscale oxides, we've been able to significantly improve the high temperature creep properties for this class of alloys. The hipped version lasted to almost 6,600 hours, and we actually interrupted the as-built GRX-810 sample at 1% creep strain at 2,800 hours to better understand the deformation that was undergoing. And so if you look at an overview of creep rupture lives compared to GRX-810 on this log scale map here with stress on the y-axis, you can see that your more conventional high temperature alloys, wrought alloys, 625, 230, 233, they all are kind of grouped together where you get a handful of hours at these low stresses, whereas GRX-810 you can either significantly increase the stress of an application and get similar lives, or get orders of magnitude longer life at the same environment. Something that I also want to point out is that most components more or less have failed by the time you get to 1% strain due to like part size constraints. And so if we looked at time to get to 1% strain, you're really reduced on the amount of time that these alloys are able to operate. 2 hours for 718, 5 hours for Haynes 230, and even our original ODS, was 9 hours. But if we look at the as-built GX810, it was 2,800 hours. The HIP version 2,100 hours, and those numbers are actually better than C103 in a high vacuum, which was 1,100 hours. And so, our hope is that GX810 can, one, replace 718 and 625 that are being used in these really high temperature applications, but maybe even replace C103 that's being used in some of the lower temperature applications, just because of how costly C103 is. We started to explore oxidation, comparing again GX810 to 718. At 1100C, you see about 2x improvement between the two alloys. But at 1200C, you see a significant divergence in their oxidation properties. 718 failed after 3 1-hour thermal cycles at 1200C, basically kind of crumbled into a pile of oxides, whereas GX810 though is losing oxide, maintains its structure and strength, and we were able to extend the test out for 100 hours on that one. We've actually recently been performing hot fire tests on GX810 injectors and nozzles at the Marshall Space Flight Center, and so we'll hopefully have those results published here soon. So far the tests have been very successful. I do want to talk about this coating process. When we started, we were coating about 1 kilogram per hour in our in-house lab scale mixers. We've been able to now get another mixer, but also optimize the coating process so that we can more or less have a coating rate of 18 kilograms per hour. And so we really do feel that this coating process that we've been using for GX810 is very robust and can be further scaled to maybe introduce other oxides. I do want to say this is I think a great case study of how additive can infuse new materials much more quickly than conventional processes. We started printing GX810 for the first time less than 2 years ago, and we're already to doing component hot fire tests at Marshall. And so that's I don't think you would be able to do that type of rapid development with any other manufacturing process. I do want to touch on the fact that we are also doing refractory alloy development here at NASA Glenn for a multitude of applications that most people are probably aware of: hypersonics, fusion or fission power, and we've also started coating refractory alloys to explore types of improvements and properties that we might see here. And so this is some early work that my colleagues Justin Milner and Eric Brizes have been doing on C103 and ODS C103. And what they've been able to find is that when we incorporate these dispersoids into C103, you're able to significantly improve its strength compared to non-ODS versions. And so if we look at these room temperature curves here from the left to the right, look at those yellow dots, you can see almost a 40% increase in its strength. And so not only can these dispersoids improve nickel or nickel cobalt chrome based alloys, but we do think it can obviously improve a wide range of different alloy systems. And then lastly, I would like to just show that we were able to 3D print that original combustor dome that kind of kicked off this whole project, and we actually just finished the first series of hot fire tests on that part, and it did not fail the way that the other parts have failed, which was usually through catastrophic cracking. And so we're hoping to also write that report up here pretty soon. And so I'd be happy to answer any questions and discuss AM. Thank you.
Great, thank you, Tim. And I'd like to thank all of the panelists today. And we have a couple of questions to jump into, so I'd like to invite Jamie and Doug back as well to join us for maybe addressing a couple of questions. And so to jump in, a first question, maybe for Jamie, there's questions about the environmental friendliness of powder production and that sort of thing. You addressed it briefly, but is there more you can kind of say about that, or is there a place that people can go to look up and learn more about maybe the sustainability aspect?
Yeah, sure. So the full life cycle assessment that we did on your typical powder processing is available on the 6K website. So certainly you can reach out to any of us here to talk about it. But I think the part that life cycle assessment doesn't really take into account is the fact that we are trying to make sure that we team with all the folks that are in the additive manufacturing world. We know that there are spent powders. We know that there are waste. We know that there are some waste streams that might be undesirable and that they're not always easy to get rid of, or people just don't know really how to get rid of them. So we do like to partner with folks, and we'll take a look at what you have and what you produce and figure out the best way to get the most environmentally friendly return, which generally comes with the most value as well. Anything is better than putting it into landfill, and that's really the genesis of our manufacturing business is taking some really kind of not nice stuff in titanium, grinding swarf particulate and making it into something useful. So we have a lot of options at our disposal besides even just being able to get it back to powder. There are some other options as well. So
yeah, great. Let's see here. And I think that is an important aspect of recyclability and cost too. It's not just for environmental sustainability, but also, what do you do with the effluent if you have to spend to get rid of some of these strange materials? There's a cost to recycling as well. So addressing it is important. All right, so we have some additional questions around qualification and getting things through like FAA standards. Certainly MMPDS, which generally suggests framework for what testing needs to be done and how to test materials. That's still ongoing. The process to develop an MMPDS standard for additive. I think there's still aspects of that we really should be addressing, and I think are being addressed, but there's a lot that goes into making sure that we're farthest along. I would say NASA probably has one of the most robust standards that people typically look to, and I think part of that is because NASA started into additive earlier, because there's a lot of applications within NASA that I think are well suited to additive and to new manufacturing techniques, which is kind of the point of NASA as far as I'm concerned. Of doing new things and approaching things in a new way before others do. But we're actually seeing quite a bit of adoption outside of NASA and space applications now. We're seeing, we have an application, and one of our largest applications is in F1 racing and their engines. It's actually quite high volume. There's, I would say, we end up having more scrutiny in F1 racing than we do actually in a lot of flight hardware, which is surprising, but it is someone's life, and there's a lot of eyeballs on that. So there's I think a range of different places and ways that people are going about qualification and qualification of additive as a new technique. I don't know if anyone wants to jump in on that, but we do have quite a few other questions. So we'll move to the next one. There was a question about,
before we go, this is the NASA 6030 standard. It's available for the public. It's released to the public, so you can pick it up, and it basically has your qualified manufacturing process for additive in here, including all the testing, characterization, NDE that needs to be done. So I would encourage people to read this if they want to know about the gold standard for using additive parts. Although it doesn't apply to all materials and additive manufacturing techniques. I think that's also important to identify. Yeah. You can quickly push the boundaries of your materials and your manufacturing techniques and get outside of the NASA 6030 standard. But for laser powder bed fusion, it's fantastic.
Yeah, and certainly I would say that it is an incredibly strict standard that goes above and beyond a lot of other standards and other places that are putting things together. And maybe that's because it was the first. So it is, I think, if you're looking to have everything locked down, the NASA standard generally is above and beyond many of the other standards, and maybe to its detriment is then hard to actually achieve. But then if you are able to achieve the NASA standard, I think there's a lot of robustness behind it. One of the other questions that we get, and actually as Elementum, we get this question a lot, Tim, but can you talk to the dispersoids and the stability of the dispersoids during printing? And I certainly have comments about that as well.
Yeah, you know, we do know that, you know, with the coated powder, you have to make sure you print with parameters that allow for the dispersoids to be evenly dispersed. You know, issues that you have to pay attention to is, you know, you want to make sure that you aren't getting agglomerations in your part that could be, you know, initiation sites for, you know, cracks to form. And so I think we have a pretty good grasp of that with what we've been doing with GRX-810. I will say, you know, in terms of stability of oxides on testing, they're very stable. After looking at, you know, microstructures at 1100 C for 3,000 hours, you know, you see very little evolution of those oxides. And so, you know, it's one of the, you know, main reasons why you see such improvements in the mechanical properties is that, you know, they don't evolve when you're at those temperatures.
And I think it's one of the key differences, at least for the RAM technology. And again, I don't want to get too far into the Elementum products in this setting, but because of the formation in situ of the ceramic particles, that is one of the advantages of that dispersion mechanism, is the formation of the ceramic particles in situ. But I found actually that the nanoparticulates, such as what GRX-810 is doing, because of the steric attachment the nanoparticles onto the larger particles, it is quite stable. And we found that reuse is generally, you know, that's everyone's first question, generally is quite stable.
Well, you know, when we started out, it was a very small project. And so we got, you know, 100 pounds of powder. And so all of those properties that you're showing, you know, wasn't done with, you know, the first use of the powder. It was all done with recycled powder. And so, you know, we've recycled powder up, you know, 20, 30 times and haven't noticed any issues in terms of, you know, lack of oxides dispersed or a big drop off in mechanical properties. That being said, we do want to do a very robust recycling study, you know, in-house. We'll hopefully have some of those results here soon, but nothing has, you know, shown up in our testing or characterization that would suggest there would be an issue there.
Yeah. Well, I think, you know, we have quite a few more questions, and I don't know that we'll be able to get to all of them, but maybe we take one or two more here if we have time, Patrick. So I wanna dive into maybe philosophical questions of the standards that say exist with NASA or exist around the you know, standards for a specific alloy system. Do those stifle innovation or do they actually support innovation? Doug?
Well, I mean, that's a good question. I would say that, like you said, you know, the standards are rigorous and they're designed for safety and mission success. So, you know, you have to have standards that you follow to be able to, you know, have confidence in your parts. That being said, you know, when you're producing things, you know, like metal matrix composites or partially reacted alloys, functionally graded materials, bimetallic materials, it's very hard to apply standards because, you know, how do you do a heat treatment regimen or tension and fatigue testing on a functionally graded alloy where you might have, you know, 100 intermediate compositions that transition from one material to another. So it is, you know, the standards that we have, they're very rigorously applied to powder bed fusion parts, depending on what classification those parts are. But clearly moving forward as we go to exotic materials, multi-materials, metal matrix composites, functionally graded alloys, there's going to have to be new ways to qualify those parts for service that take into account the fact that they cannot be conventionally qualified using your standard coupon testing. And that's something that we haven't, yet figured out completely. Typically what we'll have to do is qualify a particular part for a particular application. And it may not be a part that is like a structural part. It might be a part that's got magnetic properties. So it will probably involve a lot of full system level testing on the part, where you actually, fabricate your part, you make 5 of them, and then you go through the qualification process for all 5. But, does it stifle innovation? I mean, you don't want to fly things that are unsafe, so you want to have standards, but at the same time, having the standards then puts a somewhat of a barrier to infusion. So that's what I'll say.
Yeah, I'd say in our experience as Elementum in developing new alloys, we were actually almost craving some standard to at least be shooting for, because I mean, you could do so many things. I mean, we've printed probably over 150 different types of alloys, from tweaking different alloys to different levels of ceramic to different base chemistries. But ultimately, we have to know, well, if we need to fit within a standard so that people actually use it and go into production, that really is the gap that we're trying to cover, right? Which it's not that you can make something cool that has properties that are great once, like we had with stir casting, and when I was doing my PhD, you could get it once, but not the next time. With 3D printing and really going after some of these standards, if you can do something repeatedly and be able to develop a full data set, that's really where it gives us something to shoot for and go for, rather than it just being kind of blah everywhere. So at least for
fortunately,
me,
if you're dealing with powder bed fusion, the NASA 6030 standard is a well-defined standard that you can apply, any material and go through the whole process. So that's one thing that we've been able to do, is go through the whole qualified manufacturing process from powder all the way through part. And that can be applied to then any material that can fit in powder bed fusion. So at least with monolithic materials, there is a process in place that is well defined, and any material can go through that process and be stood up to flight qualification with that standard. It's the DED processes and the multi-material processes that are much harder to do.
Yeah. And so final question, there's a question about, post-processing and how do you develop materials with the entire process. I think we've seen a lot in the past where it's, well, here's a material that should work really well. We can print it, great. And then you move on. But what about the additional steps of how do you machine it? How do you heat treat it? How do you qualify different heat treatments and find the best heat treatment? There's quite a bit to go down there, and we found certainly with many of our alloys is we're designing them with the most simple heat treatment possible. And so it's that last statement of or qualifier as possible. Tim, have you found a similar kind of direction? And what are you using to dial in the heat treatment?
Yeah, so specifically on the ODS alloys, alloys like GXA10 or nickel cobalt chrome, what's nice is there aren't any precipitates that you have to age out to get to the properties that you want. And so the fact is that your best properties are actually in the as-built state. But obviously there's applications where you have to have a hip step to close up any defects that might have shown up. And so we've done a few different hip cycles just to make sure that you always get a really nice closing of any porosity that might have shown up. But beyond that, there isn't really much post-processing. We are actually doing a machining study as well on these ODS alloys in-house, so that hopefully soon we could say, hey, if you want to turn this material, this is the what you can expect. If you want to EDM it, this is what you can expect, and things like that. So
great. So I know we have quite a few more questions and a bunch of people. It's great response. I think and we could get down some rabbit holes on some scientific discussions with the group we have here. But I think you know, there's a lot to, I think, take further, and I want to make sure that we are recording this and we will share the recording. Certainly the data for Elementum products is on our website. I expect that there's other places that they can find information about the products that you all shared here today. And then certainly we will be sharing, I think, contact information for everyone here as well. So if you have additional questions or want to follow up, we'll make sure that everyone has access to everyone here on the webinar. But I'd like to take this time to say once again, thank you to all of our panelists. And I've really appreciated it. I think this has been a great webinar. So we'll continue this series of webinars of Bridging the Gap. We'll do about 3 a year, as we've been continuing to do now for the past 2.5 years. And so please be on the lookout for the next one. So thanks, everyone.
Thank you.